Hello, thank you for being here. We are going to talk about remote shells and edge routers. Not a good combination. So let's start with a brief introduction about ourselves. So we are Stanislav and Francesco. We are security researchers at Scout Vedere Labs, where we do vulnerability research and some threat research. So I will start with the motivation and background part, then I will let Stanislav present to you all our findings. So we have been looking at edge routers for a while, and these devices are sitting on the edge of the network, and they face internet and give access to the corporate network. And last year, we did some research on Sierra Wireless cellular gateways, where we found 21 vulnerabilities and a critical remote code execution. We also looked at firmware of 5 different IoT, OT edge routers, where we found many issues as well, such as lack of binary hardening, outdated software components with known vulnerabilities, custom security patches without any kind of documentation, and again, the use of default credentials. One of the main reasons we decided to look at this topic is that threat actors are really interested in exploiting this kind of devices, since they are the perfect entry points into business networks. Indeed, attackers can do any kind of malicious activity, often without being detected. So this year, we decided to select a vendor of edge routers that seems like a bulletproof target, since it has a lot of past research. And this vendor is DrayTek. So they have more than 4 years of active patching, and they frequently publish security advisories. There is also a proven interest from threat actors. Despite all this research and this exploitation by threat actors, we were still able to root a device through an unauthenticated remote code execution via a textbook buffer overflow. This happened again, and it took us about a month of work. But yeah, what is DrayTek? So it's a well-known Taiwanese manufacturer of network devices. It was founded in 1997, so it has a quite long story. And they sell devices from simple small office home routers to complex VPN concentrators used by businesses. And these are some screenshots we took from their website, where they claim that their devices are secure, so they run a proprietary and closed operating system. They are feature-rich. They provide VPN, firewall, content filtering, and they are ISP approved. Indeed, there are many internet service providers that use these devices. There is also this success story about the cross-nation healthcare system in Saudi Arabia that decided to adopt their solutions. So we have already mentioned that there is a lot of research. Indeed, DrayTek has published 13 security advisories in the last 6 years with over 100 historical CVEs. And typically, when a vendor is transparent about vulnerabilities and publishes them quickly, it's a good sign of a mature security team. However, new research and new findings keep popping up over the years. As an example, there were recently 2 interesting talks targeting DrayTek. So, one by Philippe Lorette, where he found a critical remote code execution a couple of years ago, and another talk at DEF CON. Besides researchers, DrayTek is really popular among threat actors as well. So indeed, in 2018, threat actors changed DNS setting on DrayTek routers using a 0-day vulnerability, and OS command injection was exploited by a Chinese APT as a part of a malware campaign. In 2022-23, some end-of-life DrayTek routers were targeted by a Chinese malware. And another report suggested that the goal was reconnaissance against the US Department of Defense. Around the same time, DrayTek devices were targeted by another threat actor known as VoIP Typhoon. And very recently, before the publication of our research, so in September, the FBI announced it had taken down a botnet exploiting 3 historical CVEs. So there is also another valid reason why threat actors are targeting DrayTek. So look at the numbers. When we did our research, there were roughly 700,000 exposed DrayTek devices on Shodan, with over 400,000 exposing their management interface on the web, even though DrayTek discourages to expose it for obvious reasons. And in any case, you can see that the vast majority of these devices is located in Europe, especially in UK, then Asia and Australia. So the problem is that many of these devices may be vulnerable. And in this slide, you can see that many internet service providers are using DrayTek devices. And this is an interesting analysis done by Census on our research, where they try to quantify the impact on internet service providers. And we can see that the ISP that has the largest number of devices is in Taiwan, while in Europe is in UK. So we have seen many reasons to target DrayTek. And we typically do research on devices and software overlooked by other researchers, so that have fewer competitors. In this way, we can maybe find more vulnerabilities and in general have a better return on investment. In this case, we have seen that several critical RCEs and command injection have been found in recent years, and that a lot of patching has been already done. So we wondered if we could find more issues and whether a threat actor would still be firing at the same target. So once we decided on the vendor, we had to select the proper device. And DrayTek offers different kinds of devices. They really have many models, from simple bare metal routers that run real-time operating system to complex and powerful security appliances such as the VPN concentrators. And nowadays, modern routers are basically mini servers. So they have lots of hardware resources. There are Linux, they have virtualization support. They often support containerization through Docker as well. The problem is that many of these devices are poorly hardened. They have default software that enables living on the LAN techniques. And these virtual machines can be exploited if they are poorly implemented, poorly designed and implemented. Indeed, a vulnerability in a complex and popular device offers a larger return on investment for threat actors, but for security researchers as well. So typically, a router is a simple hardware box that runs some kind of embedded Linux distributions with custom binaries and scripts to implement more functionalities and features. And this is also called router OS. You probably know OpenWRT. The problem, again, is that everything often runs as root, and you can imagine that an exploit on this kind of devices could be really devastating. A new generation of routers has started using virtualization since 2010, for example, Cisco routers. And this led to these so-called complex routers, such as the Vigor 3910, which we selected as a target. And this model runs on Ubuntu Linux 64-bit as a host. Then all DrayTek devices run a proprietary operating system called DrayOS. But on more complex Vigor devices, DrayOS runs in a virtual machine, while the host is still Ubuntu. The virtualization is supposed to add a layer of security and to ensure reliability, since it can restart really quickly after error conditions. On top of that, some Vigor devices can run an intrusion detection system, such as Suricata, and other software through Docker to achieve greater extensibility. So basically, this looks really great, but we wonder how this is actually implemented. So now let Stanislav explain you how this is implemented and all the findings.
Thank you, Francesco. So I'm going to take you through the technical part of this talk. And before I proceed, I just want to say that all of the conclusions or the errors are our own, and these are only our opinions. Right, so this is just an overview of what we found. And in total, we found 14 different vulnerabilities, which belong to different types and classes, also commonly known as unforgivable vulnerabilities. Goes from the paper by Steve Christie from Mitre, published in 2007, where he explains typical software flaws. And we found all kinds of stuff like weak encryption, credential reuse, copy-paste code, which led to serious issues like bad input sanitization propagated all over the place, and plenty of buffer overflows. And on the right, probably you cannot read it, but it's an excerpt from the same paper about unforgivable vulnerabilities. And here, it's sort of a historical model that shows a typical vulnerability maturity of a product in terms of the recurrent vulnerabilities. So from 1 means the most obvious one, and 7 most sophisticated one. And based from what we find, we actually classified this one to be at the phase 3 only. So it's pretty immature, unfortunately. So before we started the research, we needed to basically find some target. In this case, we decided to go directly with reverse engineering the firmware, which is available on the vendor website. Unfortunately, as they always do, they encrypt it and they add some fancy packaging all over the place. This time, we just decided to follow the past research, and basically, there is information on how to decrypt the firmware available for some time, and in this case, no keys or algorithms were changed, so we just were able to create our own decryptor and get the clear text firmware image for one of the model, which is 3910. At the time for the lab, we could only buy 3912, which is more advanced, more modern model. Unfortunately, for this one, something has been changed, so we could not easily decrypt it yet, but we were able to do it using one of the vulnerabilities, which I will show you later. So the router operating system is huge. Actually, it has a lot of components, so we had to start somewhere, and naturally, we decided to start with the most obvious component, which is web UI. This is the admin interface. Immediately when we started, we realized there is already an issue because there's a single set of credentials for everything, for the web UI itself, for all the services you have running on the ports, and even for the host operating system, it's the same admin credentials here. So very nice. A few words about the web UI. It's a standard web admin interface. You can see the screenshots here. It's used to configure and manage the device remotely. The manual for the device explicitly states that you must not expose it to the internet, but we also, the previous slide with 400,000 devices, so naturally people do not really follow that advice. And one of the critical issues discovered in the recent past for DrayTek was, it had to do with this login form here. So it was a buffer overflow with the login or the password field itself. So yeah, we decided to have a proper look at this one again. Immediately when we looked at the web UI itself, so the client side, we found some patterns of input validation issues. And on the left upper corner, you can see a form that you can fill in. And basically, this is a way to customize a welcome message for the router. So basically, every user that will log in will see something else. And there has been a vulnerability in the past about this. So you could actually add JavaScript code, and it will be added to the web page. No questions asked. They have added a function that sanitizes the input, but unfortunately, they did not consider all the possibilities of including JavaScript code, which we took the advantage of. And in this case, we could get stored cross-site scripting easily. Another example you can see at the bottom, in this case, we could inject JavaScript code directly in one of the form parameters, and this particular parameter is their implementation of the CSRF token, which is a little bit ironic. But yeah. So we found a bunch of other client-side issues, and then we moved on to just looking how the authentication works. So as I mentioned, the same set of credentials are used across the entire system, so that must be important and must be really hardened. Unfortunately, they don't really enforce transport layer security, which is the HTTPS protocol. So normally when you just navigate to the router using the IP address or the domain name, you'll be using HTTP by default. And this is problematic because when you actually log in, all the credentials are transmitted practically in clear text. So it's base 64 encoded and URL encoded, but yeah, you can reverse that and you can read the credentials. So technically, if anybody can sniff your network traffic, yeah, they can own your device easily. Still, we can easily fix that by using HTTPS, and that can be configured through the web UI itself, so everything should be fine, right? The devil, as they say, is in the details. And so the TLS is only secure where you have enough entropy to generate private keys that will be exchanged by client and the server. And there was a very nice paper from Ali Abbasi and Jos Wetzel a few years ago, and they basically show how difficult it is to have a proper source of entropy on embedded systems. For that reason, there are different trade-offs. One of them is a mechanism called pseudo-random number generator, which is a deterministic algorithm that, given a sufficiently random input as a seed, it will produce a random enough output, which can be then used as a key material. In the nutshell. But then if you can guess the seed, then you can also determine the algorithm and you can guess the output, and that basically means you can also reconstruct the private keys and break the TLS encryption. And that becomes a problem if your credentials are transmitted like this. And if you look at how it was actually implemented, we found that they are using OpenSSL library, but they are using a very old deprecated API, which is not considered to be secure anymore. Moreover, TPRNG was indeed seeded with a random string, but not the one that you would normally expect. So for those of you who is not familiar with OpenSSL or the way TPRNG works, this is basically the equivalent implementation that I found on XKCD website. So yeah, you can technically reconstruct private keys and steal the password. But then this is all theory. Let's look for the buffer overflows, and we found lots and lots of them. So the web UI itself contains a lot of pages which are implemented as C functions because it's a binary. And almost every of them had a buffer overflow of some sorts. At some point in time, we decided to stop documenting them because there were too many. So we had to divide them into classes. And the most common one that you can see here is basically a web form variable that comes from the GET request, and then it just being copied verbatim into internal data structure without checking its size. The other one was a bit more complex. It had to do with unexpected sign extension or integer overflows when calculating the size of the copy. And then our favorite shotgun parsing, where you basically have a huge piece of code that parses large data structures coming as an input and then populating some internal data structure without validating the input in the first place. And with those things, we already saw you could have different kinds of impact. You could get semi-controlled writes into different program sections, mostly BSS, where all your static variables are located. You could get different kinds of denial of service because this thing is virtualized. If something is crashed, it restarts in a matter of a couple of seconds. But if you override the entire program through a huge out-of-bounds write, then it will not be able to restart, and somebody has to pull the plug physically, which can be a problem if the device is located somewhere in a remote location. So you have to actually go there to do this. And of course, we identified some of them as potential remote code execution, but we had to understand if it's really the case. At this point, we were still quite early in our research for this target, so we had to think what we will do next. We only had, realistically, only a bunch of buffer overflows and still a lot of other components to explore, like the VPN functionality, different protocols it supports, and other things. At the same time, in these kind of devices, buffer overflows are difficult to exploit. And here's my favorite citation from Stack Overflow, where they say basically, tough luck doing that in the virtualized environment. But at the same time, we are researchers, and the threat actors, they don't really care. So they are indeed interested in novel vulnerabilities and novel ways to attack things, but they will be fine with the buffer overflow, probably. So we wanted to see if, at this point, basically, we can mess this thing up with what we already have. And that has become our new research question, so to speak. And next, I would like to show you one of the vulnerabilities that we use to do exactly that. So this one is a classical stack buffer overflow, and it has to do with the URL itself. Most of these web pages within WebUI call a special function that parses the query string parameters. And as a refresher, you can see query string, an example of a query string at the bottom of the slide. It's basically the portion of the URL that comes after the question mark. And it's used to pass different parameters and arguments into a web application. So it has keys, values, and those are separated by the equal sign, and individual parameters are separated by the ampersand. So in this case, there was a destination buffer allocated on the stack that should hold pointers to all of these different parameters as they arrive, as they are being parsed. And of course, because it's on the stack, it has fixed length. And yeah, classical problem, nobody checked if it can actually hold all the parameters provided by the user. So in this case, because every web page is using that logic, you can trigger it by navigating to any of the 100 pages available on the device. And in this case, you can basically have indirect arbitrary write into the stack. And here I will just explain why I said that. You can see on the right a very schematic description of this, it's a schematic depiction of the stack, just when the overflow might happen. And you can see there's a query string buffer somewhere on the stack on the right. And below we have the return address. And basically, as the query string is parsed, for each element, such as the key and the value, you will have a buffer allocated on the heap. So it will be somewhere there. But the pointer to these elements will be actually added here on the stack into this query buffer. So basically, it's an array of pointers to these elements. And as you can see here, if you add enough of these pointers, you will eventually overwrite other variables, some other stuff, and the return address. And if it's not something meaningful, then it will crash. It may look different or weird to some of you, and that's because it's actually ARM64 system, but it runs in 32-bit mode. So in this case, you have 64-bit code, but the address of the function or the pointers will be only 4 bytes. Right, so once we found this very nice write primitive, of course we had doubts if we can exploit it, so we looked under the hood to see how this DrayOS is actually run and what it looks like. Turns out the entire operating system is just one binary. That is literally all DrayOS, including the web UI that we just saw. It's run through modified chemo executables, and those binaries could be also interesting target for the research, but we didn't go into that direction yet. As far as binary protection go, there is no data execution prevention, which means we can directly inject shellcode into the stack or onto the heap wherever we want. Naturally, there are no stack canaries or heap canaries, which prevent you from doing that. It's not a positional independent executable, which means we know exactly where every function will be in the virtual memory, and same goes for the stack and the heap because there's no address space layout randomization. So for those of you who have never saw that, the picture on the right basically summarizes the defenses we found. And yeah, basically it's a completely flat binary that has everything we need and no protections whatsoever. So it's an easy mode for us. Still, we found some challenges that we never expected. And the first of them is that when we were looking at how to trigger this issue, almost every of these web pages actually required an authentication token before it starts to process the query string. So that was already a problem because we wanted to put unauthenticated remote code execution into the vulnerability description. And the second problem was even bigger, and we call it, it's called this free CTRL name function. Basically, what it does is that when the function that parses the string which we want to overflow, when it exits, it will call this function, which is essentially a chain free. So it will take the address of this query string buffer and it will start freeing all the pointers to the keys until it encounters a null pointer. So it doesn't have any size, it will just going to keep forever until it finds a 0. And after it does that, it will also zero out the address on the stack. So basically, even though we can achieve the overflow and override the return address with something we want, it will zero it out in the end, and all we get is a crash. That's a problem. And this is also a good example why researchers should spend a little bit extra time analyzing the exploitability of their findings, because that actually might be the case. Still, we were quite determined to go to black hat, so we decided to spend a little bit more time, and in a couple of hours we found actually a very, so out of this 100, there was 1 or 2 pages in which they did not require authentication to process the query string, and I suspect that's because of the copy-paste code, so something has been shifted. And the second lucky coincidence was that there was a local variable located just below the return address on the stack, and it was explicitly initialized to 0. So in that case, when that nasty function that I just showed you will be called, it will stop at this local variable, and it will actually leave our overwritten return address alone. So we actually achieve what we wanted to achieve, and that's great. With that out of the way, the exploit looked very simple. So this is a proof of concept in which, to take the advantage of this vulnerability, you need to send a GET request to this vulnerable page that I just discussed. Add a bunch of ampersand characters to make sure you fill the stack in the right way. And then there goes your shellcode, and in this case, because they have a function that decodes URL in a funky way, you can just inject the shellcode directly. And in this particular case, all it does, it just prints a certain message to the serial console. And we can either loop it, or we can just recover, and it will not even crash. So in this case, it was easy to make it not to crash. That's cool, but it's not interesting at all. So we decided to see if we can do something useful with it. So in this case, as a reminder, we're still within the VM, so we cannot pop any root shells, unfortunately. We are only there at the moment. Still, because it's a flat binary that has everything, we can do quite a lot of things. So threat actors did things like DNS hijacking to reroute traffic or to serve some malicious content. You can change any settings of the device that you want, just overwriting the memory in the right place. Yeah, you can make fun of defacing the web UI itself, or you can just take the device for yourself, and this is something that we are going to attempt now. So we are using practically the same shellcode. We are just rewriting a certain string in a certain memory region. And there's a video. So, second. Yeah, so here I'm logging in using the default credentials. This is just the administrator credentials that I should not know, but this is for the demo purposes, and you can see it even warns me that it's default admin password. So let's help them out. Let's just change the password for them to make sure they are secure. So basically, I'm just using another version of the shellcode that I showed you to overwrite the password directly in memory. And here I'm using the long one just to show that it's different. We copy it, and we try to log in with the new password. And it didn't even crash. And yeah, just to make sure I'm not cheating, I'm going to change the password again. And this time it's going to be 1-character password, just because we can. And it works. So virtual machines are really cool. It's really fast. It doesn't crash, so I like it. But then the title, as you may have noticed, it said remote shells. So yeah, I assume you wanted to see me popping a root shell. And that's what we're going to do. Some of the past research mentioned that there is a function that calls system commands on the host somewhere, somehow. We could not find it at first, and there are no details about this particular functionality, so we had to look ourselves. We actually found a binary on the host operating system, which is Ubuntu, that listens to different requests from the guest. For example, if the guest crashes, it detects the crash, and then it sends a command to the host asking to reboot itself. Or there are other housekeeping commands like setting the time, setting administrator, password, whatever. So all this done through a virtual serial interface, basically. And for security reasons, the set of commands that are allowed are whitelisted, so it's a game over. They definitely thought about this. And you can see the list of the commands that are allowed at the bottom of the screen. But if you look at the binary where this thing is implemented, indeed they check that the command begins with one of the whitelisted commands. But if you look at how this thing actually creates the command that then it runs, you realize that, so basically what it does, it fills that string with the command that you provide. It should start with the command that is whitelisted, but it doesn't have to end with the command that is whitelisted. And then it will be executed as system. So very simple. It's a classical OS command injection, which means we can provide the whitelisted command and then pipe something else that we want to be executed in the same instance. And in this case, basically, escaping virtual machine is hard. You need to find some vulnerabilities in the hypervisor, whatever. And we managed to escape with the VM with just command injection. And here I'm going to show an example. So this is the 3912, so the most advanced version of this device. And I'm running a netcat listener here. And at the top, I'm running the exploit to execute some commands. I'm just assigning an IP address because I'm physically connected to this device, to a physical port, and then I'm just asking nicely to give me back the root shell. And as you can see, I have to run this command several times because the exploit is for 3910, but it still works here. Something crashes sometime, but it still works. And as you can see, it restarts pretty fast because it's in a virtual machine. Okay? And now we get the root shell. You can check the operating system, everything. And from this point, basically, you have infected the host. You can install malware. You can do lateral movement, whatever you desire. And you basically own the device at this point remotely. Thank you. So Francesco now will give you couple of other findings, and he will tell you the conclusions and the outlook.
Okay, so thanks Stanislav. So now, a few notes on patches. So it's uncertain if the VM escape issue that Stanislav has shown you before was already found by Philippe Lorette, or is a completely different issue. In any case, it has been there for a few years, so it's quite bad. Then, unfortunately, we didn't have enough time to document all the buffer overflows, so we decided to report several classes of them with a few concrete examples. In our case, the vendor was really quick to release all the patches, but we are uncertain whether the fixes apply only to those reported examples. Indeed, when DrayTek published our security advisory, we saw that another one was published the very same day. And when we looked at the details of these vulnerabilities, we noticed that they look like variants of the buffer overflows that we reported. This could be a coincidence. However, when we were finishing these slides, we did an interesting discovery. So we have already seen this OS command injection. It has been actively exploited by threat actors and was patched several years ago by DrayTek. And it only affects end-of-sales models. But we discovered that on 21st of October, a researcher published 22 variants of the same bug. So we decided to have a look at the root cause, and we realized that was very similar to the VM escape bug that we just presented. It seems like they reused part of that code. You can also see here a code snippet of one of these bugs. So it seems like an evidence that no one has performed any kind of variant analysis, because all these vulnerabilities have been there for many years. Anyway, so DrayTek hasn't published any security advisory yet, And we don't know if these vulnerabilities will eventually be patched. Then, yesterday, we published a blog post about threat actors exploiting this kind of OS command injection. So if you are interested, please have a look. Now, some recommendations to device owners. So first and foremost, do not publish any kind of management interface on the internet and install updates often, especially in this case where there is an abundance of buffer overflows and many other public-facing components might be vulnerable to similar issues. Then if you own a business that relies on these devices, we recommend to perform an independent security assessment. And don't rely on the number of historical CVEs to understand the vendor security posture. Instead, use security advisories to your advantage and proactively, which means check if the same issues keep popping up over the years. If there aren't issues, if there aren't vulnerabilities, could be even more suspicious. Now, recommendations to vendors. Please, when you read about threat actors targeting your devices, make some positive change to their security posture. And it's also important to educate developers, engineers, and architects. Then, remember that firmware encryption doesn't prevent any scrutiny. So don't rely on security by obscurity to protect your products. Instead, use static analysis tools, audit the code, hire third-party penetration testers, then do variant analysis. So don't patch only issues reported by security researchers. So we have seen how this is important during this talk. Then apply binary hardening. Even if it's not a silver bullet, why not use it? And last but not least, if your software starts to resemble Swiss cheese, yeah, maybe it's better to consider a complete redesign and reimplementation of the solution. Okay, thank you very much for listening. I think we have, 3 minutes.
Yeah, if you have any questions.
Lots of those vulnerabilities look like something from an easy section on a CTF.
Yeah.
Structurally, what happened to allow that to go through? I assume DrayTek aren't necessarily unique in this sort of thing. So if these solutions are out there, we're not talking about like some complex cryptography, just simple, length validation. Why haven't these been in place for so long?
Yeah, it's hard to tell because we are not DrayTek. We have only view from the outside. I would probably say, yeah, because nobody bothered to do it.
Okay, well, thank you.
And probably it's not economical to do security evaluation, code hardening, this kind of thing. And people still will buy it, so yeah, why waste any money?
Still 2 minutes.
Yeah. Okay, if there's no more question, we'll be outside, so yeah, we can talk offline. Thank you for being here, and yeah, see you later.
Thank you very much.